speaker is Andreas Nuyts, who will speak about Transpension, the right adjoint to the pipeline.
Thank you. So indeed, I will be talking about this transpension type, which is a novel type former that is especially relevant to type systems built on pre-sheaf models. But don't worry, you don't need to be super familiar with pre-sheaf categories to follow the main ideas in this talk. So pre-sheaf semantics, pre-sheaf models of type theory, they can model homotopy type theory, which is essentially about preservation of isomorphisms or equivalences, parametricity, which is about preservation of relations, guarded type theory, preservation of stage of computation, nominal type theory, renaming an alpha equivalence, directed type theory, which is about preservation of homomorphisms instead of isomorphisms. So all in all, I think it's clear that pre-sheaf models are good for modeling preservation properties. But as we know, dependent type theory is not just a programming language, it's also a logic, and so we would like to use these preservation properties in our proofs within dependent type theory. And of course, this is not possible in plain dependent type theory, which has simpler models also. So the solution is to add operators that internalize aspects of our pre-sheaf model so that we can use them within the type system. And the current state of affairs is that everyone has used their own operator, and there is not really a unifying theory. So we have, for example, maybe I should point here, the glue type, which has been used in homotopy type theory, but also in directed type theory and parametricity. It has a dual called weld, then there is a special eliminator for weld. There is Loeb induction for guarded type theory, which unfortunately we cannot cover in this talk. Antoine has mentioned yesterday the gel and extend types used in BCM parametricity, gel for relating types, extend for relating functions. There are a bunch of nominal operators, and then in order to build internal Kahn universes for homotopy type theory, people have used the amazing right adjoint, which is the right adjoint to non-dependent functions from the interval. And so this is a chaotic situation, and we want to simplify this, because if we have only a few type formers, a few operations that would have give us a simpler meta theory, it allows for cross-fertilization. For example, the work that I'm currently talking about made us realize that this psi or gel type doesn't really require bridge variables to be affine, which is currently required in all systems that use this. And it would also provide us some guidance in developing new type systems. For example, in directed type theory, it's not clear what should happen in all respects. So like simplifying this situation would maybe give us some guidance what to do there. And so it's known that glue can be implemented just like that up to isomorphism. And if we can strictify that, then we can actually implement the glue type. For weld, which is dual, the situation is similar, only we need a push-out type. And then everything else can basically be recovered if we have the transpension type, which is a generalization of this amazing right adjoint. So it's a right adjoint to the dependent pi type, you could say, but I'm writing for all because it can be substructural. So it might be affine or linear or whatever you want. And so from that, you can recover everything except Loeb that we couldn't recover yet. So what's our contribution, which you can read about more in our LMCS submission? Well, the main contribution is that we have a type system with you can scroll in a presentation. This is weird. Okay, I have zoomed apparently. So we have a type system which has a transpension type for shape variables. And so examples of such shapes are the interval in homotopy type theory, the directed interval in directed type theory, the parametric interval in parametric type theory, names in nominal type theory, and so on. Oh no.
Try to press F twice.
F twice? No. This is really annoying. Where am I? That is a good idea. No. Here is a zoom button. Yes, great. Fantastic. Okay, where was I? So okay, we built a type system that builds on multimodal type theory. It has pre-sheaf semantics, but unfortunately we don't have a type checking algorithm currently. And so I've mentioned MTT, other people have mentioned MTT also. Maybe I should quickly recap what it's about. So it's a fixed type system for modal type theory that is parametrized by a two category that basically specifies what modalities you're interested in. And so the objects of the category are called modes, and typically every mode will be modeled as an entire pre-sheaf category modeling all of dependent type theory. The morphisms are modalities. As has been mentioned, you can apply them to types, you can apply them to contexts, which is like the left adjoint. And semantically, these two operations will be modeled as a dependent adjunction, DRA for short. And then there are two cells, but I don't care about them today. So maybe I should specify now how we instantiated MTT for the transpension type and what are the semantics of this. And the first step is we pick some base category W. It doesn't really matter which one, and then we get a category of presheaves over that, and every presheaf category is automatically a model of dependent type theory. And so the idea is that the transpension and its left adjoint is substructural for all will be modalities. But the problem is for all binds a variable, and the transpension type depends on a variable, and this is not supported by MTT. And the solution is that we're not going to treat shape variables as variables in the context. We're going to put them in the mode. So the mode will serve as the shape context. So for example, this xi is a mode, it lists all my shape variables. And formally, xi will be a context modeled in this presheaf category W. I've said that modes will be modeled as presheaf categories, and so this mode xi, I'm going to model it, and you don't need to understand the category theory, but I'm going to model it in the presheafs over the category of elements of xi. What counts is what it means, and so I can do type theory in this presheaf category, and basically the judgments in this model are equivalent to judgments in type theory over just W, except that I have to prefix all these judgments here with the shape context xi. So basically what I'm doing here is I'm arranging stuff that so that doing type theory at mode xi means doing type theory in context xi, which is exactly what I want. Now I have been talking about shapes, but I've not actually said what a shape is. The most simple situation is when the shape is Cartesian, then I just pick an object in my base category, which is required to be Cartesian then, and so then I can multiply by this object U, which gives me an ender functor on W. I want to be substructural, so I'm going to generalize this. I'm going to more generally pick a base object W. The category need not be Cartesian, and then I will require that there is an arbitrary functor to multiply with U, which sends the terminal object to this object U. And an example that uses this full generality is a twisted prism functor by Pignot and Krauss, which is relevant for directed type theory. This multiplier will extend over the Yoneda embedding to an ender functor on my presheaf model that allows me to extend shape contexts with a shape variable. And I'm going to assume that this multiplier is a local right adjoint, which means if I restrict its image to the slice category over U, then I need there to be a left adjoint. And these two adjoint functors, they lift to the categories of elements. And it's the fact that if you have a functor between base categories, then you get a triple of adjoint functors between presheaf categories. So now I get two triples, but because I started from adjoints, the middle two coincide. So I get four functors in total, which are like a substructural existential, fresh weakening, a substructural for all, and then this transpension. The latter three can be internalized as modalities, and the former three are then the logs for these modalities. Some shapes might allow weakening if they are structural enough. So then I get a shape substitution here, which lifts to the categories of elements, which gives me a triple of adjoint functors, which I can interpret. And these are really the standard semantics of the sigma type, weakening, and the pi type. And then the latter two can be internalized as modalities with the former two as their logs. So what's very strange and not so good here is that weakening is now not implicit. It's a modality, so it's really a type former. So there will be no implicit weakening over shape variables in this system, unfortunately. And what's good to mention is that if your multiplier is Cartesian, then the fresh becomes meaningless. So fresh weakening is equal to weakening, and the substructural for all is equal to pi and left adjoint to this transpension type. Weakening is just one example of a substitution. I can consider general shape substitutions. The situation is entirely the same. I get two modalities here, among which a substitution modality. So again, shape substitution is not something that you can compute and pushes through your type formers. It is a modality, so it is a type former, so that's annoying. And then to conclude, so what we find is that we can recover most internal presheaf operators that people have been using from just three: the transpension type, the strictness axiom, and some pushout. And the basic ideas of the semantics of the transpension type are actually fairly straightforward. And the take-home message is, of course, that you should absolutely check our preprint, which is on the archive. So thank you.
Thank you. Yeah, very interesting talk. I not sure if I understood everything, but I'm wondering, since you're introducing a new type here, what are the, like, do you have some typing rules for it, right?
Yes, so it's...
Because you're talking a lot about the semantics, but
yeah,
I would...
yes. So here, right. So it's an instance of modal type theory. So what really happens, and I'm using a funny notation here, but what really happens is you have like the modal introduction rule. So the transpension type is just a modal type for the transpension modality. And so if I introduce it, then what I get in the context is I lock by the transpension, and the lock for the transpension is the left adjoint. So I basically apply for all to the context, and I actually gave the lock here the name for all. So this is a indirection to make it more conceptually clear what's happening. But so this is really literally an instantiation of MTT. This is just a modal type. And then elimination can be done by the co-unit of the modality. So you can prove if the modality is an internal left adjoint, then the projection is as powerful as the pattern matching elimination of the modality.
I see. And then a follow-up question, because you said you don't have a type checking algorithm yet.
Yeah.
So what's the problem with implementing these rules?
So in order to type check MTT, one thing you need to be able to do is decide equality of two cells between modalities. And currently I have no idea how to do that. And then another issue is that I've added a few primitives on top of MTT, for example, to reason about boundaries of shapes. So for the homotopy interval, this is basically 0 and 1, but I wanted to consider that a bit more generally. And there it's completely unclear how substitution even works. So yeah, these are the challenges. Yeah.
Thanks.
Any other questions?
What was this strictness axiom?
It's basically but the slide is not that useful actually. So it's basically the glue type by an isomorphism. So you have a type that exists everywhere. You have a partial type, and you know when a partial type exists, both are isomorphic. Then you can like strictify, so you can complete the partial type that is so that it's everywhere isomorphic to the one you started from. So it's basically glue as it is used in cubicle hot, I guess. Yeah.
Are there any other questions? Okay, then let's thanks.